My programming language of choice for this is Python, and I'm using Sublime Text on my Mac, but you can use whatever is good for you. I wanted to show you how to program this because a lot of this gets lost in the theory. When people study finite elements, generally at the end there's some big project at which point the programming is all dumped on you. And I think it's far more intuitive to go step by step along the way and have some programming examples, and then this will give you a framework for the future. So following on from the previous video, we want to construct some arrays, and for this I'm going to use numpy, which is a package in Python that has numerical calculations. And let me save this before I get started. Just call it FEM bar. Good as anything. Okay, and I'm going to start off by defining a method called bar, which will take a parameter num elements. And then it's going to do something. Okay? And we will run that by typing bar and calling that function or that method. Okay, and the idea is from the last video, you know that we have a mass and stiffness matrix. Mass matrix looks something like this. It's rho times A times length divided by 6. And then this is times something like 2, 1, 1, 2. Okay, and then similarly we have a stiffness matrix for the elements. And by the way, I'm using a lowercase l here because I'm denoting the length of the element, not the length of the bar that we're modeling. And the stiffness matrix looks something like E times A divided by L times, and then this is 1, minus 1, minus 1, and 1. Let me just put this down at the bottom so we can reference it. So the methodology here, if we follow on from the last video, is first of all, we've got the element mass and stiffness matrices for a bar. Let's just put some comments. Element mass and stiffness matrices for a bar. Then what we need to do is construct the global matrices. So construct global mass and stiffness matrices. Then we need to do the assembly of the individual elements. And then finally, we need to remove the fixed degrees of freedom. Write that out. And then solve the eigenvalue problem. Okay, so I'm going to go now and fill in a bit of meat on these comments. Starting off with defining the mass and stiffness matrix. And for this, we say that M is equal to numpy array of, this is going to be a 2 by 2, so let me do it like this. And this is 2, 1, 1, 2. And we've got to divide that by 6. And if you go back to the last video, you understand that we just eliminate these material properties, material and geometric properties, if we include the area and length. And we do that by just putting the number, substituting a 1 in for them now. We realize eventually we'll need to scale it by these parameters, but if you look at the way in the previous video that we handled this, you'll see why it's okay just to ignore it for now. All right, so the mass matrix, we've got to account for the length, the changing length of the element. If the length of the element is a half, meaning that there are 2 elements, then what's going to happen in the case of the mass matrix is you actually need to divide by the number of elements. They've got to multiply. So let me write this out and then I'll go back and just explain it again. But similarly for the mass matrix, for the stiffness matrix, it's MP array of, we do the same thing here. But in this case, it's 1, minus 1, minus 1, and 1. And we are now going to multiply this by number of elements. And because number of elements is an integer, we want to convert that to a float first. All right, so what we did is we took these formulae down here, and I accounted for the fact that this assumes a unit length. So if there are two elements, that each length is a half, therefore we need to divide the mass matrix or each element by the number of elements. For similar reasons, we multiplied the stiffness matrix by the number of elements. So I'm going to erase this. Okay, and moving forward, we've done step number 1. Step number 2, construct the global mass and stiffness matrix. Well, we start off by creating a matrix that is the correct size, meaning it's got the right number of degrees of freedom, and we fill it all up with zeros. I'm using a capital M to denote the global matrix as opposed to little m and k, which are the element mass and stiffness matrices. So this is NP zeros, which, just as you might imagine, fills the whole array up with zeros. And what are the dimensions? It's the number of elements plus 1 by the number of elements plus 1. Okay? There's always 1 extra degree of freedom versus the number of bar elements you have. And in the case of the K matrix, we do exactly the same thing. Okay, so that's that step done. Easy. Assembly of the elements. This is a little bit tricky. So what we need to do is we need to loop through each element. So I in range num elens. What we want to do in each case is we want to create a temporary mass and stiffness matrix, just like we did here. In fact, I'll copy this code. And in this case, we'll call it mtemp. These are temporary matrices. And the idea is I want to create a temporary matrix. I want to take that element and I want to place it in that matrix. And then I want to add that matrix to the global matrix. It will become clear in a second. So I create a matrix full of zeros, the same size as the global matrix. Now I want to place the element in this matrix. So I want to say something like m temp is equal to m. Only m and m temp are different dimensions. So I need to be clear within m temp rather, where I want to place these. And let me write this first and then explain it. So it's I to I plus 2, comma, should be a little I. Again, I to I plus 2. And remember, this range is I and I plus 1. It does not include I plus 2. So we're saying for element 0, which is your first element, it should go from node 0, which is your first node, the 0 is the index, until the first one. Let me just write that in there. Exact same thing for k. So we say that k temp is equal to k. So I just want to be clear that what it does for each element is it takes this temporary matrix of zeros, and then it takes the mass or the stiffness matrix, and it places that within a 2 by 2 section of the temp matrix. And this is a 2 by 2 section because it goes from I to I plus 1. Remember that I plus 2 is not inclusive. And again from I to I plus 1, which is a 2 by 2 matrix. Okay, enough said there. And finally, we just want to add these to the global matrix. So the global mass matrix plus equals m temp. And similarly, the stiffness matrix plus equals k temp. Okay, and we are done with the assembly. That's how simple that is. Now we want to remove the fixed degrees of freedom, which in this case is just node number 1. The index in case of Python is 0. In every array or every list, the first item has got an index 0. So let me go up to the top here and I'll say restrained degrees of freedom, and we'll just create a list. In this case, it's only the first one, but in general, you could add more. And we must go through here and remove them. So we say for DOF in restrained DOFs, what do we want to do? We want to take M, and we want to say it's equal to numpy.delete M. What are we deleting? Whatever that column or row is. And the axis tells us whether it's a column or a row. So axis equals 0 means do it for the row. Axis equals 1, we'll do it for the column. So I'm doing it once for the row and once for the column. We do the same thing for K. Okay, and then this is K, and then this is K. And I'm going to just neaten up my code a little bit by saying for I in range 0, 1. And then I'll say this is equal to I, this is equal to I, and we can delete these. Just a little more compact. All right, very good. Now finally, we want to solve the eigenvalue problem now that we have our mass and stiffness matrix. Well, for that, we use a package called scipy and a function called eigh. So the function is eigh. There's also a function eig, which is more general than eigh. Eig allows for complex eigenvalues, where eigh recognizes that you're dealing with matrices that are positive definite and symmetric, and so those yield real eigenvalues. So this is a little bit more specific. We'll use eigh, and we need to import it at the top. So from scipy.linearalgebra import eigh. And then we just say eigh of mk. I did it backwards, km. And that will actually return the eigenvalues and eigenvectors. So we can just catch them like this, eigenvalues, eigenvectors, and then we have that. Boom. That's how simple it is to solve the eigenvalue problem once you have your mass and stiffness matrix. It's one line. And you can do it for any number of degrees of freedom, practically anything. All right, so moving forward, we now actually want to calculate our frequencies. And our frequencies are just our eigenvalues. We take the square root of it. So we use numpy. And remember, numpy operates on an array element by element. Okay, and I misspelled frequencies. And now finally, we just want to return, let's see, we'll return m, we'll return k, we'll return the frequencies, and we'll also return the eigenvectors. That's it. That's our routine done. All right, so now how do we actually access this routine? Well, let's test it first. Let's go down to the bottom here and type in bar. Bar needs to have a parameter, 1, and we'll print it. Or in fact, we don't want to print it. We want to say, since we're returning all of these, that is equal to bar 1. And why don't we print frequencies? Let's run it and just see if it works. Oh, syntax error in line 16. That needs to be a colon. Do it again. In line 36. Oh, of course, I don't need the range in here because this is a list. Oops. Fix that. All right. 1.73. So there, it worked. What if my bar was 2? I should have 2 eigenvectors and eigenvalues. And if it's 10, look how quickly this runs for 10 elements. There we go. And it determines our frequencies. So, well, why don't we do something a little bit more detailed here? Let's run it for, let's do this. For I in range from 1 to 10, so 111. Okay, and in each case, what we're going to do here is we're going to say bar of I. So I'm going to run it for, oh, gosh, I'm fighting this. I'm going to run it for 1 element, for 2 elements, for 3 elements. Each time I'm going to run this, I'm going to get the frequencies at this point is all that I'm interested in. All right, and then let me print that out. So print num elements frequency, and then error. and that's a percent. Dot format. The number of elements would be I. This would be frequencies 0, since we just want the fundamental frequency, and I can write that here, fundamental frequency. And then this would be the error. And the error I've got to calculate here. In fact, let me add the math library here at the top. Okay. Because just before we start, I'd like to say, this is where the code starts here, by the way. I'm just going to close or compress that. So I'd like to say exact frequency. And we know this from the exact solution. This is the answer to a classical problem, is just pi divided by 2. So math pi divided by 2. That's the exact frequency. So the error would equal frequencies 0 minus the exact frequency, parentheses, divided by the exact frequency times 100. Okay, and I'm just going to round this here to 3 decimal places. Same thing with the error. And then at the end, I'm not going to print frequencies, but let's print the exact frequency. In fact, we'll print exact frequency. Let's run that. Exact frequency. I think I'm missing a bracket here is what's the problem. Evex is not defined. Did I make a typo? It looks like Evex. Okay, there we go. So that works. So let me just clean this up a little bit. And what does this show me? With one element, the frequency is 1.732. We know the exact result. We can round that to 3 places. So the exact result is 1.571. And look how we go from 1.73 down to 1.572 over the course of 1 to 10 elements. In fact, if we look at the error in the fundamental frequency, with one element we get to 10%. That's pretty good for one element. But by the time we have 4 elements, we're less than 1% error. In fact, just to make this a little bit clearer, why don't we plot it? And for that, we'll use matplotlib. So from matplotlib, import pyplot as plt. Okay, do this down here, right at the end. So what we want to do is we actually want to store the results. So why don't I have results here? Results, we'll create a list, and then over here, we'll go results append, and what we want to append is I as well as the error, so the number of elements as well as the error, and we want to do that as a tuple, so we put brackets around that. If you don't know what a tuple is, you should just brush up on some Python. It's beyond the scope of this class, this video, but I'm sending it as both these values. I'm storing in that array. And then eventually I want to retrieve those values from the array. And the easiest way to do this is we'll say the elements is equal to, let's see how to do this. We want to create a list where it's x0 for x in results. But we want to take that list and we, whoops, what did I do? We want to take that list and put it into a numpy array. So np array of this. Oh, that's a mouthful. Okay, and then we want to do exactly the same thing for the other part of the tuple, which is the error. So we'll say errors is equal to now x1. Let's just line that up. All right, so we'll say plot the results. And now it's easy. Plot, plt.plot, elements, comma, errors. And let's put a marker for each point and connect it with the lines. Okay, plt, we want to set the x limits on the x-axis between, well, from the lowest number of elements to the highest. So it's elements, open bracket 0, to elements minus 1. Whatever the first and the last number is in the elements array. And then let's just put some labels. Number of elements. Plot y label is the error, which is a percentage. And finally, let's show the plot. That's it. Okay. So again, I took the exact result. I've then created a results list where I've stored all my results. And then eventually I'm hoping to plot it. So let's run it. And if I've done it all correctly, which is unlikely, then this should all run. And there we go. It ran. So what we're looking at is the error from 1 element to 2 elements, from 3 to 4, the error in predicting the fundamental frequency. And it's clear that once you get to about 4 elements, your error is very, very small. In fact, it's less than 0.5%. So you could use this to determine just how precise you need it to be. And obviously, as you add more elements, it puts overhead on your system. But even at 10 elements, and this is not compiled code, it's script Python, it runs very, very quickly in the blink of an eye. Let me run it again just to prove the point. There you go, just like that. So I hope you found this video useful. If you did, please go ahead and give it a thumbs up so that others can get to see it too. Thank you for watching, and I'll catch up with you in the next video. Bye-bye.